Hi, this is Jason Baker, and welcome back to our Week 6 lecture on all of the different AWS extra services. And the next service I wanted to talk about is Elasticache. Elasticache is a distributed in-memory caching system. Well, what is a distributed in-memory caching system, you're probably asking yourself? Well, remember back earlier in this course when I talked about the sort of relative differences in access speeds between accessing memory versus accessing disk versus accessing network. If you recall, I mentioned that one of the challenges that we can experience when we scale our applications is if those applications are accessing disk and if they're heavy I/O applications, that disk I/O can become a serious bottleneck. And so anytime we can access data in memory versus accessing it in disk, we can significantly speed up the performance of our application, or we could significantly scale the performance of our application and handle greater demand in customers. So the benefit of the Elasticache service is that it allows you to store data in memory. And if you can store that data in memory, your application can perform much faster. We use Elasticache oftentimes to cache frequent database queries. For example, you might have a database that is storing a list of corporate store locations. And it's unlikely that those corporate store locations change all that often. Maybe you're adding a new store a week or a new store a month if you're one of these, fast growing companies. But in the whole scheme of things, that data isn't changing very often. So instead of hitting the database on disk to pull that data, why not store those corporate store locations in a caching system? The same thing for product listings. You can oftentimes store those in a cache as well. When customers access a website, they are generally provided with some sort of session ID, which is sort of tracking the user request and is providing a stateful experience for that customer. Maybe they only have to log in once on your website and they get a session ID, and from that point on, the session ID serves as the sort of a token that the user passes and it represents their credentials. Well, instead of storing that token in a database and hitting the database every single time the customer makes a request to your website, you can store that information in a cache, like an Elasticache. The Elasticache service supports two different types of cache engines, and both of these engines are very commonly used by organizations who are building extremely highly scalable platforms. The first one is called Memcache, and Memcache is a very reliable key value store. Its primary benefit is that it's very simple to operate and use. And the second engine is Redis. Redis is considered to be more featureful. It supports a wider variety of data formats, and not just key value, but also lists, arrays, sets, and sorted sets. The negative on Redis is that it's a little bit more complicated to work with than Memcache. But the reality is that both of them are widely used, and my organization uses Redis pretty extensively. One of the other benefits of Redis is that it can support a master-slave replication architecture, and you can deploy Redis nodes across multiple availability zones, which gives you greater redundancy. That's not possible with the Memcache D engine. Here's a quick example of what a Memcache D request looks like. Now, this is a request that is being sent directly to the Memcache D service. So it's connecting to Memcache D on port 11211, and the application is connecting to the service and saying set a create a key called A and set the value of that key to the value hello. And Memcache D responds back saying that that value was stored. Then the application makes another request and it says get the value of A, and Memcache D responds back with the value of A, which is hello. If if the application requests the value of B, the value of B hasn't been set yet, and Memcache D uh, responds with a cache miss, and essentially doesn't respond with any sort of value. So you can see that Memcache D is very, very simple. You're just simply creating keys and assigning keys values. You can then make a request to Memcache D for a key, and Memcache D will respond with the corresponding value. That's all it does. It's very, very simple. Again, the benefit is that it can it can retrieve the value of keys extremely quickly. And so we're talking like thousands and thousands of retrievals per second, and much faster than what a database could do. Of course, this is much simpler than something like a relational database, right? A relational database uh, is storing tables containing tuples, and it's doing join operations across tables and so on. This is just a key value store. And here's a quick Redis example. In this example, the application is setting the key A and is setting it to the value hello. Redis is responding back with OK. And again, the application is getting the value of A and Redis responds with hello. Very, very similar to Memcache D. Pretty much everything you could do in Memcache D, you can do in Redis. And Redis allows you to do actually much more as well. So that's uh, that's Elasticache. We use it to accelerate the performance of our applications by storing certain sets of data in memory instead of on disk. Now, I should note that the data is actually still, in most cases, still stored on disk. Uh, the application just isn't reading it from disk. It's trying to read it from the cache first. If it finds that data in the cache, then it uses the data there. If it doesn't find the data in the cache, then it may go on and try to find it in the database. Okay, our next service is the Simple Notification Service, or SNS. And the Simple Notification Service allows us to publish messages from our applications and deliver those messages to subscribers. Now, when I say subscribers, I mean that sort of in a general sense. A subscriber could be a person, or a subscriber could actually be another application. So you got to think about this in terms of uh, one application component talking to another application component. You could have one application component which is publishing a message, and that message is then being delivered to a subscriber, which is a second application. The simple notification service can deliver messages using a variety of different formats and services. It can deliver messages via email, SMS text messaging. It can do mobile pushes using the Apple and Google, Fire OS and Windows mobile push mechanisms. It can push messages into something called an SQS queue, which I'll talk about shortly. And it can also push messages to an HTTP endpoint. sort of like a webhook in the sense that it's going to push out this request to a specified URL. So how does SNS work? Well, you start by creating a topic, and the topic is sort of like the access point that our application or service will use to publish to. And when you create a topic, you associate it with multiple publishing endpoint types, the email or text messaging or the HTTP endpoint. All those I just talked about uh, just a minute ago. The application publishes messages to SNS, to an SNS topic, and those messages are stored in multiple availability zones within a region, and that provides redundancy for those messages. The recipients of these topics have to subscribe, or the recipient of the messages have to subscribe to this topic that we've created in order to receive the messages. And this is really key thing to understand about SNS. The messages are pushed out to the recipients that have subscribed to the topic. The application will send out an email message. It'll push out that email message, or it'll push out the text message, or it will push a request out to the HTTP endpoint. SNS is a push-based service. Well, why would you want to use SNS? We can use SNS a variety of ways. We can use it as a trigger mechanism. An application experiences some sort of event, and that event triggers a push, a message to a person or to another application component. We can use it for things like auto scaling notifications. We can send an auto scaling notification to an SNS topic, and then that message could be sent to another application, and that other application might trigger that other application to perform some task, or maybe that sends an email message or a text message to a member of our operations team. The next service is the Simple Queue service. And the Simple Queue service is sometimes confused with the Simple Notification service. And I'll try to help you understand the difference here. So the Simple Queue service is a distributed queuing system, and it allows us to take messages that are generated by one system component and place them on a queue where they might be consumed by another message component. This allows us to essentially decouple different components or different parts of our application. What's interesting, and if you recall back earlier in this course, the Simple Queue service was the first web service launched by Amazon back in 2005. Why was this the first service? Well, this actually is an incredibly important service because it allows us to support sort of asynchronous application integration. It supports a number of different application messaging patterns. In this case, a very common pattern is a producer and consumer pattern where we have application components which are producing messages or producing work, and that work is then placed on a queue where it is then eventually picked up by a consumer, or sometimes we call this a worker. And the worker can pick up the message or pick up the work and perform some sort of task. The problem that we would get into if we didn't have a queue in place here is that if we directly coupled the producer components with the consumer components, the producers would be sending messages directly to a consumer. And it's possible that we would overwhelm the consumers. We might not have enough consumers available to handle the messages, the work that is being produced by the producers. What that means is that the producers might back up. They might not be able to send work to the consumers because the consumers are blocking any additional incoming work, and that would mean that our producers essentially can't do anything. It would uh, if these were customers trying to place orders on our system, they would effectively be halted because the producers could no longer take any orders. And so this is a very, very common pattern to introduce a message bus, a queue that between our producer components and our consumer components. And this allows us to queue work up, and then the consumers will pull messages off the queue as they become available. So, what are some use cases for this SQS service? Well, there's all kinds of different use cases. Anytime we want to sort of asynchronously pass work from one component in our platform to another component. For example, if a user uploads images to our website, maybe we want to create thumbnails or we want to watermark those images. We don't want the customer to have to sit there and wait for our application to generate thumbnail images. We can just ship that work off and put it in a queue and let some separate component in our application, like a worker component, pick up that message and then generate thumbnail images for a customer in the background. Same thing with video transcoding. If you've ever uploaded a video to a service like YouTube, you'll see that you upload the video and then YouTube will begin transcoding that video in the background, and you can continue uploading additional videos or watching videos or so on. So it's happening asynchronously, and it's happening by some sort of video transcoding worker. We can use SQS to support payment process workflows in ordering systems. This is one of the reasons why Amazon, focused on SQS first. If you think about Amazon's business, there's queues everywhere. There's asynchronous transactions. There's payment and shipping workflows. So a lot of their business really depends on these sorts of queues. It's absolutely essential to their platform. Well, how does this SQS service actually work? Well, what happens is you have an application component, and that application component generates a message. And think of a message as being, it could just be like a small JSON object, it could be a small amount of data. That message is placed on the SQS queue. So it's sent to the SQS service, and it's placed on a message queue. That message then, at some later time, is pulled from the queue by another application within your platform, or another component. And I emphasize the word pull here because this is really one of the major differences between the simple notification service and the simple queue service. If you recall, the simple notification service will push messages out to subscribers. With the simple queue service, the messages are being pulled by these consumers, by these workers. They're being pulled off of the queue. Once the consumer pulls the message from the queue, it's going to perform some work, and it then has to delete the message from the queue. And I want to walk through this process real quick because it's a very, very interesting an interesting process. So in this diagram, you can see we have a component in our application platform. That component is going to send a message to our message queue. And each one of these objects here represents a message. When the message is on the queue, each message has its own visibility timeout clock. So each message has has the data that's within the message, and then each message has a visibility timeout clock. So the message is just sitting there on the queue, and it's waiting to be pulled. If we go down to the next step, we have a second application component. And a second application component goes out to our message queue, and it pulls down a message. So it pulls that message off of the queue. And when it does that, this visibility timeout clock starts ticking. Okay, this is like a countdown timer. In this case, it's gonna wait 40 seconds. So the timer starts the moment this second component pulls down that message. So the second component, application component, it processes that message. So it might go and perform some work based upon whatever is in that message. And when it's completed the work, then it will delete the message from the queue. Now, while it's processing this message, the message is effectively invisible. It's technically still on the queue, but no other consumers, no other workers can see it. It's sort of like disappeared from the queue. It's no longer visible. However, and so when the second component, when it finishes its work, it can then delete the message from the queue. So it'll then at that point be permanently deleted from the message queue. If the second component does not complete the work, by the time this timer runs out, by the time it hits 40 seconds, then that message becomes available on the queue again. It becomes visible on the queue. So what sort of problem do you think this might cause? I'll let you think about it for a minute. And this is the situation. The message was pulled off the queue by a second component in our application. That application is trying to work on that message. It's trying to process it. But while it's processing that message, the visibility timeout clock expires, and that message becomes visible on the queue again. Well, the biggest problem is that now that message, while it's being processed by that consumer component, could end up back on the queue again and visible on the queue, meaning that it's possible for a second worker component or consumer component to pull that message. And now you have two different workers that are trying to process that message. So SQS guarantees that each message that will be placed on the queue will be received by a consumer at least once, but possibly more than once. What that means is that any sort of action that we take on a message should be idempotent, meaning that if you have multiple workers who are processing that message, every worker will output the same exact result. If you have an image that's been uploaded by a customer and you have multiple workers that are generating a thumbnail of that image, then the multiple workers they're just going to generate the exact same thumbnail. One worker is going to create the thumbnail, and then a second worker is going to create the same thumbnail and maybe overwrite the first one. but the end result is the same. It doesn't matter how many workers are simultaneously processing that message because they're all going to end up with the same result. Now, you wouldn't want to do something like run a bank transaction through this type of queue because you would have two workers that are making changes to your account balance, and that's not going to be idempotent. So, because one worker is going to change the balance and the other one's going to also change the balance. So they're both going to subtract or deduct from your account or add add to the balance of your account, and that's not an idempotent operation. The worker components are generally trying to pull that message queue um, every few seconds to see if there's anything in the queue. You can imagine there might be times where the message queue is empty. There's just nothing in there. And so you have these worker components, these consumer components that are sort of constantly polling the queue to see if there are any messages there, but there's really nothing there. I have an example here where if a consumer component was polling the message queue every 5 seconds, sending a single request every 5 seconds, that single component would be making over 500,000 requests a month to that queue. And the SQS service, in terms of its billing, is partially based upon the number of requests that are made. So if you just have 4 backend components, you're generating over 2 million requests per month to that message queue. And that can be really wasteful because, maybe there are times where the queue is empty. So there's really no messages to pull. Well, to sort of counteract this sort of excessive polling, you can enable a feature called long polling. And with long polling, what'll happen is your application will make a request to the message queue and to ask and see if there are any messages available. And instead of closing the connection to the message queue, it can maintain an open connection to that queue for up to 20 seconds. Any new messages then that enter the queue can be streamed then to your application. And this can greatly reduce the number of requests that your application components are making to the SQS service. Well, one of the questions that people oftentimes ask is there a way to prioritize messages within a queue? You have an application component, it puts a message on the queue. What if we want certain messages to be prioritized higher than other messages? The SQS service doesn't have any concept of message prioritization. So the pattern that we use to solve this issue is simply to create multiple queues. We have, in this case, we have an example where we have a priority queue and we have a secondary queue. Our application then can sort tasks based upon the priority. For priority messages, will just simply be put on the priority queue and secondary messages on the secondary queue. Then we can sort of allocate more resources to the priority queue so that those messages are processed more quickly than the secondary queue. You might have a case where you just simply have more EC2 instances or workers that are pulling messages, or maybe the workers are going to try to pull messages from the priority queue first. If they don't find any messages there, or if they have excess sort of time, then they'll pull messages from the secondary queue. We can also sort of integrate both the SNS service and the SQS service to create this sort of fan out um, messaging bus. And that allows us to parallelize some of our tasks. Here's an example where we upload a cute baby picture to the website, and our web application then sends a message using the simple notification service. It sends a message to a set of SQS queues. So the SQS queue, the SQS service can be a consumer, or it can be a subscriber for an SNS topic. So this image upload is going to trigger a message which is sent simultaneously to 3 different SQS queues, and then each SQS queue is going to perform some work. One of the queues might generate a thumbnail, another one is going to do image recognition, and a third one might actually scan the metadata, or sort of update the metadata on the image. So this is a way we can combine both SQS and our SNS queues together. And okay, our next service is the Simple Email Service, or SES. A simple email service is a scalable email service that AWS provides, and it allows applications to both send and receive email. Well, why would AWS provide an email service? Well, the reason is because as a customer of AWS, you are not allowed to run your own mail server on an EC2 instance. They block by default the SMTP port, and that's because they're trying to reduce fraud. They're trying to minimize the amount of spam email messages that could be potentially sent by customers. Because what would happen is that spammers would buy stolen credit card numbers, and then they would sign up for services on AWS. They would launch an EC2 instance running their email spam software, and then they would send out millions and millions of spam email messages. So AWS just simply bans customers from running their own email servers within EC2, and in lieu of that, they provide you with this simple email service. The billing for the service is based upon the number of messages you send and receive each month. They allow you to send up to 62,000 messages free uh, through the SES service, and they also sort of limit you to a certain number of messages that you can send per day. But these AWS limits can be increased over time if you make a request to their support team. The next service is Route 53, and Route 53 is a DNS, or domain name hosting and registration service provided by AWS. Now you can go out to a domain registrar and register your domain name. And there are like literally hundreds of different domain registrars available on the internet. You can also register your domain and host it with AWS. And the Route 53 name is based on the famous Route 66 highway that crosses the United States. And in this case, the 53 comes from the that's the well-known port associated with domain name services. Now, some of you might not be that familiar with domain name services, but it's really an absolutely critical part of our internet infrastructure. What DNS allows, or what DNS provides, is a translation service. It translates domain names like yourcompany.com into IP addresses. When you type in a website address like www.google.com into your web browser, a DNS service has to translate that name into an IP address, and your web server, your web browser is going to be communicating over the internet with that IP address. Here's how DNS works. So you have your client computer. This is sitting in your home or your office, and you make a request to www.yourcompany.com. That request is first sent to a DNS server, and this DNS server might be hosted by your internet service provider. The internet service provider might not know what IP address is associated with www.yourcompany.com. And so it will send that request to a root DNS server on the internet, and there's a bunch of them. The root DNS server might not know the IP address for www.yourcompany.com, but it knows who knows. So it responds back to your ISP's DNS server and says, hey, why don't you go talk to this top level DNS server? It knows the domains for all the .com domains. And so your ISP's DNS server talks to the top level DNS server, and that top level server says, well, I don't have the IP address for www.yourcompany.com, but I know the server that knows that information. So it responds back to the ISP. The ISP then goes directly to the name server that is hosting the DNS information for yourcompany.com, and that name server responds back with the IP address. Then your internet service provider's DNS server responds back to your web browser, your web client, with that IP address. So all of that is happening in the background when you make any sort of request using a domain name. And it's pretty remarkable how many systems can be contacted to get that information. Now, once the ISP's DNS server finds the IP address or is told the IP address for yourcompany.com, it will cache it for a certain period of time. That way, when your system asks for that IP address again at some point, it doesn't have to go and talk to all these other servers. It's already got that information cached, and your local system will also cache that information as well. So that's how Route 53 works. And if you recall, earlier in the course, we looked at different patterns for, sort of distributed patterns. And one of those patterns was a tree structure, a tree pattern. And this is the DNS service implements this sort of tree distributed request pattern. So I mentioned that using the Route 53 service, AWS can serve as both a domain registrar and a name server. So you can register your .com domain name with Amazon, and then you can create name server records. And those name server records are the records which map the domain name, the host records in the domain name, to the actual IP addresses. So that the name server is really the authoritative record holder for a domain name. You can create different types of records for a name server. You can create something called a start of authority record, which specifies the name of the administrator for the name server. You can create address records, and the address records are records which actually map host names to specific IP addresses. So you could have a host name like www.mycompany.com. The www portion is the host name. You can have that mapped to a specific IP address. You could create a CNAME record, and a CNAME record will map a host name to another fully qualified domain name. So you can think of a CNAME as being kind of like a way of aliasing records. And then finally, there's a special record type that's available in Route 53 called an alias record. And this is like a CNAME record, but what's really interesting about it is that it can point to dynamic AWS targets, meaning that you can point an alias record for a domain name at something like an Elastic Load Balancer endpoint. That way, and this is how you can point customers to your Elastic Load Balancer as the sort of entry point to your application. If you point www.mycompany.com to the Elastic Load Balancer endpoint using an alias record in Route 53, then all of your customers' requests will be sent to that Elastic Load Balancer, which will then turn around and distribute those requests to various web servers that are associated with the load balancer. We can also create routing policies within Route 53, and these routing policies are really important. We can use these policies to distribute traffic across multiple regions by providing dynamic DNS responses based upon the policy configuration. What this means, and this is really important, what this means is that we can use Route 53 to provide geographical redundancy across entire regions. Remember, regions are partitioned into availability zones, and there are many types of ways that we can distribute requests across availability zones. You can set up a separate EC2 instance in each of AZ, and then configure a load balancer to distribute requests to each of the instances. You can set up RDS uh, to to create a cluster of database instances in multiple availability zones. So that's a fairly easy problem to solve. But what if you're concerned about the loss of an entire region within AWS? You can use the Route 53 routing policy to reroute requests from one region to another region. The when you create your Route 53 name service records, it implements a default routing policy, and that default routing policy is called the simple policy. The simple policy just simply maps DNS responses to a single region. It's the simplest policy that you could set up. You can also create a weighted routing policy. And with a weighted routing policy, Route 53 will distribute traffic across multiple regions based upon a weighting that you assign to each of the regions. And for example, you might tell Route 53 that you want 85% of the DNS requests to route traffic to the US East 1 region, and you want 15% of requests to be routed to the US West 1 region. And this is all happening via DNS. Customers are making requests to www.yourcompany.com, and 85% of your customers are going to get sent to your website that's hosted out on US East 1. And 15% of your customers are going to get sent out to US West 1. And your website could be the same on both regions, and you're synchronizing data between the two regions. So you can use this. Uh, you can use this to sort of distribute requests across entire regions, across multiple regions. You can also use this for A/B testing, where maybe you're rolling out a new feature and you want only a small portion of your customers to be able to access your new site. And you're sort of testing their responses to the site. You're watching the performance metrics on the site to see that your customers are experiencing good performance. You can use this weighted routing policy to sort of carve off a portion of your traffic and send it to a different region for testing purposes. You can create a routing policy that's based on latency. And the latency routing policy uh, allows Route 53 to distribute traffic to the lowest latency region. And this can be important from a customer experience perspective. For example, you might want customers located on the East Coast of the United States to be directed to the US East region, and you might want European customers to be directed to one of the European regions. The Route 53 can kind of determine where your customer is coming from, and based upon their and and it can determine which region is the lowest latency region for that customer, and it can redirect that customer to that low latency region. So this is based upon speed and performance. Route 53 can implement a failover routing policy whereby Route 53 is monitoring the health of your services. And if it sees a failure in your services, it can then redirect customers to a secondary region, like a disaster recovery region. An example is you might have your primary website and your service running on US East 1. And if there's some sort of disaster with US East 1 and the region fails, there's sort of catastrophic failure, then Route 53 can detect that failure and then redirect customers using DNS to the secondary region, to the like a US West 1 region. And then finally, we can set up a routing policy based upon geolocation. With the geolocation routing policy, customers are directed to a specific region based upon their physical location. And this is a little bit different than the latency routing policy. Remember, the latency policy is going to direct customers to the fastest region. That might not necessarily be the closest region in all cases, or it might not be a specific region. With geolocation, we can make sure that like all queries from European customers are handled by a specific European region. And the reason why you might want to use a geolocation routing policy is because you need to meet some sort of regulatory or data privacy requirements. And there are different data privacy requirements in the European Union versus the United States versus Mexico versus Canada, etc. And so there might be you might have some strong requirements that you have to meet and ensure that if customers are providing data to your application, that data might need to reside within a specific geographic region. Here's an example architecture of showing how we might use Route 53 to, to deploy a disaster recovery service. In this architecture, we have our active service that's running in US East 1 in North Virginia. You can see that Route 53 is taking in requests for our website, which is awsdrdemo.com, and is sending those requests to a load balancer within a VPC. And that load balancer then is distributing requests across multiple web servers in a web server pool. Maybe this is an auto scaling group. The web servers are communicating with a backend RDS database instance. That RDS database instance is mirroring, it's replicating its data with a secondary database instance running in a different region, in this case, the US West 1 region in North California. Now, if there's some problem with this application, if there's some problem with the region, then that health check will trigger Route 53 to begin redirecting requests to the secondary region. It will now redirect requests to this load balancer, and then the secondary application can continue to support customers in the case of a primary architecture failure. This is one of the reasons why Route 53 is so powerful, because it allows us to support and deploy our application across multiple regions.